So when we're done with calculating the bottom hole pressures, the first thing we actually need to do is to pick which of the bottom hole pressures that we like to use for further analysis, where bottom hole pressures obviously are used. So that will be in an analytical RTA setting, or in a numerical RTA setting, or for history matching, material balance exercises, etc. And once you calculate your bottom hole pressures, you see that there's a few different ways of looking at the data, and actually automatically the software provides the smoothed results. So if you just look at the smoothed results, it's just a very simple smoothing filter that's added onto that data. So if you like to use more smoothed data, you can do that. That can be very helpful in cases where you control the well on the wells flowing bottom hole pressure, and then especially the water rates tend to be causing some sporadic changes in the calculated bottom hole pressures, and that's typically because water is actually one of these things that are not very well metered in the field. However, in this case, you can, if you want to, use the measured pressure directly as well, or any of the calculated pressures. What we're going to go ahead and do in this case is just to keep the measured pressure right here. But if I would change this to, for instance, voltage monitoring IR, and I go to the numerical RTA feature, for instance, you'll see that that changes to the voltage monitoring IR. And if I do, if I change it to the voltage monitoring IR smoothed, and I go to numerical RTA, we see that I get the smoothed version of that. So it looks much smoother. But again, we'll just go and use the measured data in this case, and go ahead to go to the numerical RTA exercise. And here we need to provide some information of the fluid initialization and rel perms, and that information has been provided here in the onboarding page. So just download that somewhere locally on your computer. Open that file for information, and then as you'll see in that Excel sheet, you will have 3 different sheets, and we're going to use each of them, but just for the fluid initialization in this case, use 600 GOR, and then 38 for the water saturation. And then the initial pressure we've already set, so just save that. All these other properties that you saw here are just calculated automatically. So it's for 600 pressure, this is the saturation pressure. And if I change that to 500, for instance, that will give us a different saturation pressure. So that's just automatically coming from the Blackwell tables that has been calculated from the fluid definition part of the work that we did earlier. Now, if you like to do the matrix relative permeability inputs, we see that there's just default queries inputted here. So here, just going to the rel perm page, put in 0 under conic water saturation, and 0 under SGC, and else than that, just keep everything else default. Then the next thing that you'll go ahead and do is just to click Run Infinite Acting. Here in practice, you can actually change grid refinement, so you can do an even lower grid refinement, and then it will run even quicker, or higher when if you want more resolution. And you can also change your dimensionless fracture connectivity, but in this case, we're going to just keep it constant. So I'll go ahead and run this case now. That might take 30 seconds or so, but just while that is running, we're providing fluid information here. We see that saturation pressures are changing, etc. So the question that might arise here is, where are these, what are the PVT properties that's used for this? And again, when we did this fluid definition job earlier, where we provided the GOR and the associated reservoir conditions with this process, actually what's automatically then been happening behind the scenes is that we've created this Blackwell table here automatically. And that Blackwell table feature provides you an overview with the initial conditions of that particular fluid at initial conditions. It also shows the plots of the different properties in that Blackwell table, and you can look at that in a tabulated format as well. And of course, you can then export this into any third-party platform if you'd like to do that as well. I think what's important to emphasize here is that these black hole tables are representing essentially all the PVT properties that are used in the different features where PVT is required in the software, whether that's bottom hole pressures, RTA, material balance exercises, history matching, etc. Another thing that's important to emphasize is that these tables are so-called modified black hole tables. So they have the so-called solution CGR term, or also called the vaporized oil ratio, which takes into account the condensates that is in solution with any potential free gas in the reservoir. So I just wanted to mention that real quick. If you go back to the numerical RTA feature, we see that the initial case has been run. We see that we're doing a decent job on our water cuts and GORs, and we should be ready to go and launch our calculation in the numerical RTA workflow, which is clicking this button right here. So in this case, we're actually then launching not only one, but 12 different reservoir simulation activities in the cloud at the same time. Each of those calculations, the only difference between the different calculations is the so-called tank size. So each of these curves will provide different type curves, which is what we're going to use when we are going to perform this so-called numerical RTA workflow. So what we've actually done now very efficiently is to do 12 of these reservoir simulation activities in parallel on the cloud. And for now, you haven't actually learned that much about the so-called numerical RTA workflow, and that will save for later. But now I just want to show you some of the mechanics of how that works. So the first thing that you need to pick in the numerical RTA workflow is the so-called LFP. So in this case, an LFP of 67,500 does a very good job, especially on this type curve right here. It matches this data pretty well, and also most of the gas data. Maybe we can make it even 70,000 in this case. That makes it a little bit better. We can see a case where we make it 65,000 as well, just for the sensitivities. Yeah, maybe that was a little bit too much. So I think we can just go for 67,500 in this case. The second thing we need to do is, so here we see how the RTA results, sort of our pick for LFP and OIP, is replicating and predicting this data. So what we can do is to hold in control and then click this type curve right here. We then see that this is the type curve pick that we have gone for. And this leads us to the other thing that we need to do, which is clicking this particular stem right here. We've then picked an LFP, and we've then picked an OIP. The last thing that we might want to do is to provide some additional inputs, such that we can come up with some estimates of matrix permeability, fracture half length, etc. And I totally understand at this point you've most likely not been even exposed to the numerical RTA workflow, but yet again, this is just for us to get through some of the mechanics of the Whitson Plus software. So if we go back to this sheet right here, we see that the last sheet gives us a little bit of these data points. So that's porosity that we find right here. That's 5%, a reservoir height of 63.37 feet. The well lateral length is 10,950, and the number of fractures is a little bit more than 1,000. And these are the results parameters in this case. And it's apparently a very, very aggressive completion in this particular scenario. And I'm not going to have an opinion whether we think this is right or not, but at least the history match is it's pretty decent. And the only thing that we then could do in addition to that is to resolve these parameters and put it into the history matching module. If we click then yes on this button, we see that all the resolved parameters from the numerical RTA workflow has been seamlessly exported into the history matching module. That goes for both fluid initialization, the rel perms, and also the well and reservoir data. So the only last thing we need to do now is to run the well on the well's bottom hole pressure. And what you'll see then is that results that we'll get will be very, very close to the actual observed data, and also what we actually saw in the numerical RTA workflow. And I just emphasize again, we haven't talked that much about the numerical RTA workflow, but I'll provide a little bit of information regarding that. But at least what you'll see here is that in terms of your cumes, we're doing a pretty good job. We're doing decently on gas. Maybe we can do some additional tuning on this. But the other thing that you see here is these, high spikes in the predicted data. And that's a combination of the fact that we're using both the low grid refinement option, but probably more importantly, all these small spikes here in the bottom hole pressure that we are using. And what happens is that once you're running a well on the well's bottom hole pressure, and the bottom hole pressure is spiky and not very smooth, numerically that can cause these spikes right here. So what you can do instead is to maybe run the well on the well's oil rate, for instance, and just to redo the exercise, and you'll see that the results that you'll at least get, whether those are right or not, that's really not the point in this exercise, will be more smooth. So of course you're controlling it on the well's bottom hole pressure, so you're doing a great job there. The gas is again decent, not the best late time. Maybe we should do some additional tuning there, but at least on the bottom hole pressure, we're doing a decent job on the fit of the get-go, and also late time water cuts we're doing okay. But again, we're maybe missing something on the gas side here, so let's take this with a grain of salt. But at least the last thing we can do as a part of this exercise is to go to the forecast piece. And there's different ways of forecasting this. It's either to use a constant bottom hole pressure to the end of whatever number of simulation days that you want, or you can actually also provide a custom BHP schedule where you can look at sensitivities for all kinds of different things. But the last data point we have right here is 1381. So I can, let's say I would like to use the custom BHP here just as an example. You see that the last is 1381, and then if I just copy this and I make maybe the last data point 13, that was there already, 1381, and I click save, and then I click run, then I'm actually just running on a constant bottom hole pressure forecast, which you can do this way, or you can do by just picking the constant bottom hole pressure right here. The main point here is that we're getting some kind of forecast, so if we trust this physical forecast, then we know that this will be the results that we'll get. And here you see we're getting pretty pessimistic results. We're draining the SRV within a few more months, and there's essentially no more production to be made. So at least if we go for these results, what we can do is to go into the decline as the last thing that we can do, and that'll be the next video.